here's the second video. I'm going to do an example in the next video. So here's the second video for buckling, and I think it's a good idea to just suck it up and kind of say, okay, here's the other kind of buckling. And I introduced Euler buckling in the previous video, and we had a derivation for it. And then I alluded to the fact that there is this kind of other type of buckling, right? So that we talked about. So let me put that back up here, right? So we had this situation right here, and we said in this range up here for very long and slender, we can use this buckling equation right here. But we also note that if we and we could plot it out by taking a slenderness ratio, which is just the length over the radius of gyration. We could take that and plot it versus, we could plot the critical load divided by the area. It's sort of like a stress, right? That's really the compression stress that the thing experiences. We could plot that versus this slenderness ratio. And from a little range right here, we can see it's parabolic, right? So it's to the square, kind of inverse parabolic, right? But then we could also see for something as we get up right here, we have a material limit. So we can actually have so we kind of find, and we can find this from experiment too, that if it got a little shorter and a little shorter and a little shorter, at some point it's not gonna behave follow this behavior. So we have like a curve fit that kind of falls in here, this parabolic curve, and we call this the Johnson buckling right here. And we got to find out some place where there's a cutoff. There's going to be a cutoff where instead of doing Euler buckling, we do Johnson buckling instead. So we need to come up with an equation. So this is section 413. This is the intermediate size. So the other one's long and slender. So at some point, we're going to find a slenderness ratio where we're going to use Johnson instead, right? So if we get below this point. And so that's going to be equation 445 in Shigley. And that equation is L over K, and they decided to give it put parentheses and give it a subscript 1, is going to be equal to 2 pi squared C. Okay, now this doesn't use the equivalent length method, so we might want to we could leave that C out. If we use the equivalent length method, this becomes equivalent length, and this becomes 1, right? We just ignore it. But if we're using the C's for the thing, we use the actual length over here, and that's where, and we will use the C. And this is divided by the yield strength, and we want to take the square root of it, okay? So this is something we want to calculate, and that's really going to be, here's from other books right here. So this is like someone's showing the data right here. And so this is the cutoff line. This is the slenderness. This is the L over K 1 right here value. If your L over K is greater than this L over K right here, this limit, you use Euler. They call it long, right? If it's less than this L over K, this limit, then you use what we call the Johnson buckling equation right here. And the Johnson buckling equation is equation 446, and it looks like this. P critical over area. By the way, when we want to find the critical, we just multiply area on the other side. But we take SY minus, and then we do SY divided by 2 pi and L over K. I decided to make it capital L for some reason. Squared, and then 1 over CE. Okay. So there's the Johnson equation right there. Equation 446. Let's double check it in the book. Do I have my book out here? Yeah, I do. Let's bring him back up here and take him out. Not that you don't believe that it's there, but it's good to be seeing this in the book and in the context instead of just trusting me that I'm telling you the right thing. And it's also good to look it up yourself right here. So Yeah, so they changed some of the they changed some of the equation numbers in the 11th edition. That's one of the reasons why I was also looking right there. So it's actually equation 448. And right here he is. Right here. Here's the Johnson equation. And do they call him the Johnson equation? Okay, yeah, the Johnson equations can't be developed. Okay, so right there is the other method, right? So then, and we use that when the L over K is less than L over K1, right here. So the other equation we want to look at right here is L over K. Where'd you go? Well, they're giving some more additional equations, but we're not going to look at those right here. So here is the equation. This is 445. What did I say? Yeah, it was still 445. So they added some other stuff in between for round cross sections and rectangular cross sections. I guess they decided that was important. But this is really important. The first step that we should do when we're doing a buckling thing is to check this to see if we should be using the Johnson or the Euler. But typically Euler is for very long, and but we should check that out. Okay. Anything else I want to include in this video? It's kind of short at this point, and I kind of wanted to cover some more things. It's only 6 minutes long, so maybe I should cover what is considered short, so we can get that over with, right? So then we can get to our examples, right? So let's talk about what is a short column. What's considered short. So there's another criteria, and so this is section 415. So I will skip over these, and we'll come back over to them. I think I skipped. Okay, so if it's very short, we decided we call it a strut. So it's a short column, and it kind of makes sort of sense that as you're getting squattier and squattier, you start to get to the point where like you might get to the yield strength, right? So you might like get the stress, just the P over A of this thing might get closer and closer to the elastic limit. And so that might be something that's really going to drive whether the thing fails or not. It might be so squatty, right? So it might be right to there. Might be so squatty that buckling isn't really an important thing as much as crushing of the thing. And so that is the strut. And maybe if we want to know that where that is, this is probably from experiment. There might be some theoretical thing behind it, but we could find another point on there, L over K, to the subscript 2, right, by just taking 0.282 and AE over P right here, the load right here. So this actually has to kind of go backwards. We have to kind of know what that what the load is onto the thing. You note that because the stress is going to be from some of the bending as well, right? So this is just something that we can check later on, but I'm not really going to ask about it. But we should know of its existence, right? So but by the way, this kind of assumes that the force is going to be kind of like not down the center of the piece. So I just wanted to bring that to your attention, and I think that's enough. Right? We get enough in this video to justify its existence. So remember, we had long and slender Euler, and we decide whether to use him or not by this equation right here. And then we also have intermediate, which is the Johnson equation right in there, which is really just a curve, like a parabola curve fit that goes up to the yield strength right there. And then below a certain limit right here, which would be the L over K2, we could say it's short and squatty, so its buckling isn't really as much important as the thing is of just bending like any old beam. It's not a buckling phenomenon failure. So there we go, the end.